Hey team, it's video number 11 time for electrochemistry. This is going to have a lot of videos for this particular chapter because there's a whole lot of meat and potatoes in this chapter on electrochemistry. And I'm leaving a lot out. I'm not going to be covering batteries, corrosion, a lot of the really, really cool applications of electrochemistry. Because once you learn all this, then you can apply it to real life stuff. Right? You learn things like what galvanized means and all these really cool stuff. So when you're done, if you've got time, please, please, please read through the rest of the chapter after I get through all the meat and potatoes, and you can read the fun stuff and the cool types of fuel cells and the neat kind of, lithium ion batteries and nickel cadmium rechargeable batteries. So much neat stuff. We just don't have time. We have limited time in the semester. Too bad our semesters weren't a year. Then you could listen to me ramble on for twice as much time. Yay! We'd never graduate from college, would we? College took me 10 years. Well, I was in college for 10 years. Whatever. All right, so here we go, rambling on. Combining cell reactions. We've done this before. We did it in equilibrium where we took 2 or 3 equations, added them together to get an overall equation by manipulating, right? We could take known equations, reverse them, multiply them by 2, multiply them by a third, whatever. So that we add all those equations together, we get a new overall equation that maybe has unknown values. We did Hess's law to do that, didn't we? And there was a certain set of mathematical rules when you manipulate equations in equilibrium. Same thing in thermodynamics. We were able to add multiple reactions or equations together, but manipulate some. The mathematical rules were different though. Remember, when you reverse an equation, it's different in thermodynamics than it is in equilibrium. And when you multiply something by 2 or 3, the way you treat that mathematically was different in equilibrium and different in thermodynamics. Well, we're going to do exactly the same thing again, yay, in electrochemistry. If we have, say, a half reaction that's not on the table, we're like, I can't find it, it's not on here, crud, what do I do? Well, we could take 2 or 3 known ones, manipulate them if we need to, add them together, and if we add them together, cancel out like species, and get that half reaction of interest, we could calculate the reduction cell potential for that. Or if we reverse it, the oxidation cell, electrode potential. Cells for the anode and cathode. We're looking at just an individual electrode. Typically, we want the reduction potential because that's what this whole table is, right? We want to add something new to this table, so we're just looking for the reduction potential. So if I provide you some known ones and you can add them together using Hess's law to get the overall equation, how do we calculate the overall E0 electrode potential for that? We're going to be doing standard conditions. The problem with this is the rules, the mathematical rules for adding equations together is different in electrochemistry than thermodynamics than equilibrium. Why can't they all just be the same rules? Sorry, I didn't make the rules. So we can get the electrode potential for an unknown half reaction that's not on the table by using Hess's law to combine 2 or more, I won't make it more than 2, known reactions to get the desired one. So what I'm going to have to do is go through the new set of rules. We'll see some overlap with the old ones in thermodynamics, but there's a problem with electrochemistry. And we're going to find out when I do it on the table. You can't add electrode potentials when I take 2 equations together. Like in thermodynamics, if I took equation 1 plus equation 2, then the overall, say, delta H would be delta H1 plus delta H2, or the overall delta G would be delta G1 plus delta G2. For equilibrium, when you add them together, the overall K, equilibrium constant, was K1 times K2 times K3. Unfortunately, with electrochemistry, you cannot add those E cell or multiply them together. So we have to take it out of electrochemistry information, put it into thermodynamic information so that they are additive, and then take them back out of thermodynamic information into electrochemical information. It's a pain in the butt, my friends, but doable. So let me throw some rules up on the board. All right, kind of a cluttered board. A lot of this I put some review on here. But essentially, when you're combining half reactions to get an unknown one using Hess's law, just follow these rules and steps. Right? A lot of these we already know. Most of these we already know. Number 1, manipulate the half reactions provided You know, if you got to reverse them. If you got to multiply them by 2 or 1/2, do that. Whatever's necessary to get the job done. So that when you add those equations together, those half reactions together, you get the desired unknown half reaction that you're after, one that is not on this table. But we're going to use ones from this table that we can add together to get the one. Now, the good thing about electrochemistry, a lot of times you don't need to manipulate equations. You just add them together directly and you get what you're after. Whereas in equilibrium and thermodynamics, sometimes you really had to flip some equations around and it was like a big logic puzzle. Here, usually we just add them right together. Not always though. Number 2. And number 2 and number 3 are review. Remember, the electrode values are intensive. It doesn't matter how much you have. It doesn't matter how much water is flowing over the waterfall. That doesn't change the height of the waterfall, which is the electrode potential. So these values are unchanged. So if I multiply one of these equations here, right? If I multiply one of these by 4, 5, 2, 1/2, that value does not change. It's an intensive property. It's independent of how much you have. That makes life nice. That's not true in equilibrium and thermodynamics. If a half reaction is reversed, right? Remember, if we have to reverse one of these, you reverse it, boop, you change the sign. That's it. That's also true in thermodynamics. Not true in equilibrium, but it's true in thermodynamics. So 2 and 3 are just review. Number 4, this is where this is a pain. We need to calculate, we're given the E naught values. We have to convert those to delta G values using this equation we got, where delta G naught is negative the electron number times Faraday's constant times the E cell. Why do we have to do that? Because of this next step. Thermodynamic values are additive. So if I add 3 equations together, the overall delta G is just delta G1 plus delta G2 plus delta G3 after you manipulated those. This is not true in electrochemistry. No! Why? Why? E naught values are not additive. Essentially, you could read through why that is, not critical, but when you're doing half reactions, the electron numbers aren't necessarily going to be the same for each one. So when you add them together, it creates some issues. So they're not technically additive. So we're going to have to convert them out of electrochemical information into thermodynamic information. Then we can add them together in step 5 to get the overall delta G value for the new half reaction. Then we go out of thermodynamic information back into electrochemical information using the same equation. So the electrode potential would just be the delta G naught overall divided by the electron number times the Faraday constant for that half reaction with the negative sign. So it's unfortunate we have to go from electrochemical information to thermodynamics just so we can add the stupid things together and then extract back the electrochemical information out of the thermodynamic information. Not my favorite stuff to do, but it's doable. Let's do a quick little simplistic one. And actually, I'm going to show you a way to avoid calculating the whole thing. Because when we go from this equation to this equation, the Faraday's constant is going to cancel out, right? When you go from electrochemical to thermodynamic, and then back from thermodynamic to electrochemical, the Z's will be for each half reaction. So the Z's, they aren't necessarily going to be different, but very commonly you might have 1 electron for this half reaction, 3 for that one, 4 for that one, 2 for that one. So the Z values don't cancel out. So we got to plug those in there. And the E naught values, let me get rid of the cell there. We're doing electrode potentials there. Those are going to be different for each one because they're coming from the table here, right? So those are going to be different. The Z values will be different. But Faraday's constant's the same. So what we'll do is we'll kind of just use a little bit of algebra trick to simplify the equations and not actually calculate delta G. We'll leave it in terms of the Faraday constant times these 2 values. And then when we bring it back down here, the Faraday's constant cancels out. What? See what I do in the next problem. You can go through and do it the hard way if you want to, but I'm going to show you a shortcut. Let's do an example. All right, here's your problem. Oh, the air conditioner kicked on. Yay! Yay for air conditioning. Yay for solar panels to make the air conditioning cheaper. What is the electrode potential, the reduction potential? That's usually what we're solving for because it matches, everything we're doing on the electrode tables there. We're trying to keep everything consistent. So what is the electrode potential for the the iridium dioxide there, or iridium 4 oxide, depending how you look at it, going to iridium solid. So that's reducing from a +4 to a 0. All right. Let's say we can't find it on the table, but curious minds would like to know what it is. Let's say we find some information. It may or may not be on the table. If it's not on the table, I'll give it to you. That's not a complete table at all. Let's say we look around in some of the literature and we find that the electrode potential for the iridium 4 oxide to iridium 3, right, reducing from a +4 to a +3, is positive 0.223 volts. And we also find that the reduction of iridium 3 plus to iridium solid, going from a 3 to a 0, is 1.156 volts. So we'll be able to combine these two half reactions, or half cells, reduction half cells, to get this. I'd like to give you to try. So these are written as couples, right? So these are the reduction couples here. See if you can write out those half reactions for me and see if they combine to give you that overall one. Give it a shot. So I'm going to pause this, give you a second to think, and then I'm going to write these up on the board. How you doing so far, my friends? So what I did is I took these couples here and extracted them into an actual half reaction. So here I'm going from the iridium 4 oxide or iridium dioxide, depending how you look at it, solid, gaining 1 electron to go from a +4 to iridium +3. So it's reducing. So the reduction potential for that is positive 0.223 volts. That's my first equation. Second equation is this couple going from the iridium in the +3 oxidation state to the iridium solid. So it must be gaining 3 electrons there. So Z equals 3 here. Z equals 1 there. Do you see that? So Z equals 1 and Z equals 3. You don't need to write those down. You can just see those in your head. I'm just showing you where the Z comes from. That's the number of electrons. For a half reaction, it's just the number of electrons. For an overall reaction, it's the number of electrons transferred. And the reaction cell half cell or electrode potential for that is 1.156 volts. So I just stated what was provided in the problem as equations. So do we need to manipulate these at all? Well, if I add these together, the electrons are both on the left-hand side, so they're going to add together. So I'm going to get a total of 4 electrons on the left-hand side if I keep it like this. Let's see how the iridium 3 plus will cancel out. If I add these together, I'm after the iridium 4 oxide going to iridium solid. So if I add these together, those will cancel out, and I could do my overall equation. Let's write that overall equation down. So I will have IR O2 solid plus an electron, right? On the left-hand side, that goes away, plus 3 electrons. Are you guys okay if I just erase that and combine that to 4 electrons? Well, let's do that. So 1 plus 3 would give me 4 electrons. And that's it on the left-hand side. The iridium 3 on the right-hand side's gone. Going to iridium solid. That's what we're after. You see that? IRO2 reducing to IR solid, going from a +4 oxidation number to a 0 oxidation number. So it should pick up 4 electrons. And so we want the reduction potential for that. Oh, we cannot just add those together, my friends, like we could in thermodynamics. We cannot say that the E reduction overall is just E1 plus E2. It doesn't happen because the number of electrons are different in there. Darn the electron number! So we need to convert this into delta G, and we need to convert that into delta G in order to do this problem. Oh, darn it. So let's do it on another board. I'm going to erase this, bring these half reactions back up. And, well, I don't even need those reactions. Let's just convert them into delta G values, and then we can add the delta G values together. So pause it if you feel adventurous. Calculate delta G naught for this. Calculate delta G naught for that with that new equation we have. Please do that. All right, you can do this the long way if you want, but I'll show you the shortcut. We're not going to do this very often. Here's equation 1, the iridium 4 oxide plus the electron going to the iridium plus 3 gave you the reduction electrode potential of 0.223 volts. We got to convert that into delta G thermodynamics so that we can add them, because the electrochemical values are not additive, darn it. So I'm going to use this equation where delta G naught is just the electron number times the Faraday's constant times the E for that particular electrode at standard conditions with a negative sign. Well, Z is 1 in this case, correct? Right? Z equals 1. Boink. So I take -1, that's unitless, times the Faraday's constant, but I'm just going to leave that as F. You'll see how slick this is when I'm done. You don't have to do that, but you'll see how cool it is. Times the electrode potential of 0.223 volts. So I'm just going to take -1 times 0.223 times that. So I get -0.223 times the Faraday's constant in volts, right? Times volts. Let's do the same thing for equation 2. Let's take the iridium 3 plus 3 electrons, giving us iridium solid. That reduction potential was 1.156 volts. Let's calculate delta G for equation 2. That'll be the negative of the electron number times Faraday's constant times the electrode potential for that reduction. Well, what's Z? Conveniently lined up. Oh, I actually didn't mean for that to happen. It just happened. So Z is 3 for this reaction. It's 1 for that reaction. And it's probably going to be a different one. I think it's 4 for our final reaction, right? So take -3 times the Faraday's constant times the electrode potential. So 3 times 1.1156 is 3.468, because that 3 is exact. That's good to forsake. Put the negative sign there. So delta G is just -3.468 times the Faraday's constant in volts. I'm just going to add those two together. Do that for me. We already added the overall equation, but I'll write it up again, and then sum those two delta G's together in terms of F. Now, you could plug in 96,485 coulombs per mole if you want to, but you don't have to, and you'll see how that cancels out in a second. So do me a favor and add those together for me. Did you get what I got? Again, we're just factoring out the Faraday's constant here. You don't have to do this again. So delta G overall will be delta G equation 1, that, plus delta G equation 2, that. So I'm going to take the -0.223 times the Faraday's constant in volts, plus -3.468 times the Faraday's constant in volts. Well, let's just factor these together. So take -0.223 plus -3.468. That gives me -3.691, good to 3 decimal places, times the Faraday's constant. So I'm just factoring that, times volts. That's delta G. Now, in the last step, I'm going to take that and figure out, I'm going to take the same equation, but now I know delta G overall is this whole term. I know Z for the overall equation is 4. I know Faraday's constant. I'll just leave it as F. You'll see F cancel out. Solve for E naught reduction for that reaction. Do it for me. Pause this. Plug in this whole term into there. This will be delta G overall. You know Z's 4. You know the Faraday's constant. Just leave it as F. Solve for E naught reduction for that half reaction. Do it for me. See if you get what I got. How'd you do, gang? This is where you're going to see the Faraday's constant cancel out. So here's the overall equation again. I just rewrote that. We want to know the reduction potential for that half cell. And this is the delta G naught overall we got by combining equations 1 and 2. The -3.691 times the Faraday's constant in volts. All right, last step. We know delta G naught overall, correct? We know this. We know Z. Z is equal to 4. All right. Z equals to 4 for that particular half reaction. We know the Faraday's constant. Let's solve for that. So I wrote the E naught for that particular reduction, going from the +4 to the 0 oxidation number. So let's isolate the E naught. That's going to be, move the negative sign over, so we get negative delta G overall divided by the electron number divided by Faraday's constant. So let's bring this down. So the negative of that, -3.691, see those negative signs are going to cancel out. So I'm just bringing this whole term down, divided by Z, which is 4, divided by Faraday's constant. Do you see what I see? Faraday's constant. Bye-bye. See you later. And again, you could have just calculated through with the 96,485 coulombs per mole, and it would all just canceled out in the end. It's a little more work to do it that way still, but if you don't like this, screw it. Just do the math, right? So let's take negative, well, this is negative cancels. Take 3.691 divided by 4. I get 0.922750. Good 2. That 4 is exact, so I get 4 significant figures because I'm doing a division. Times volts. That is exactly halfway. Darn it, right? So do you round up or down? It's exactly halfway between the two. So in that situation, the last significant digit needs to be even. So that's going to round up to 0.9228 volts for that unknown reduction half cell. Cool, huh? It's unfortunate we have to take it from electrochemical, put it into thermodynamic just so we can add the stupid things together and then convert it back into electrochemical again. I'm sorry. I'm just the messenger. Oh, that video's over. Let's get into some cool stuff next time.